So let's look at another example where now this is slightly nonlinear, much easier system in some sense. So you have this x1 dot equals minus x1 cube plus some time varying function times x2. So these are all very what you call cooked up examples. So they look simple so that we demonstrate the theory, but in reality the actual time varying systems with nonlinearities could be quite nasty, and then it may take days or months to actually guess any kind of Lyapunov function candidate, right? And anyway, it so happens that the Lyapunov function that we choose is v of t comma x is equal to x1 square plus x2 square. So a note, basically, just because we are allowing v of t comma x, that is, we can depend on time, it doesn't mean that the function itself depends on time. In many cases, we may actually live with a time invariant Lyapunov function candidate. Okay, and many things come for free at that particular point, and basically the upper and lower bounds for this v of t comma x are indeed the norm square, and alpha and beta, the both upper and lower point, are identical to the norm square, right? And if you compute v dot, essentially we'll get this fourth order this thing, and then basically and a little bit of algebra there, and then we can show that v dot is less than or equal to minus norm square, norm square plus norm square times 4, and then basically this is fourth power of the norm, and that's also class K, so guaranteeing global asymptotic stability, right? So we will end up with global uniform asymptotic stability. However, in this particular case, we will not end up with exponential stability, because v dot is not less than or equal to some quadratic, but it's actually quartic, and that is sufficient to show that you will have slow convergence as you get closer to the origin, right, or closer to the equilibrium point. But of course, far off from the origin, this decreasing v dot, the way the rate of v dot is changing, it's actually quartic. So you'll have a very fast convergence till very close to the equilibrium point, but when you get close, that slows down, right? So you'll definitely not have exponential stability. So you have some kind of global exponential stability to a small region, but then after that it is simple global uniform asymptotic stability. Anyway, so each example has its own flavor and things like that, but hopefully the conditions that we applied we have in the theory can be demonstrated through these two examples. So we have seen partial stability, we have seen time varying systems, and you see that they're not too different. So now I want to show you a couple of results where we ignore the stability aspects. We don't care about the equilibrium, if you perturb something, but it's simply boundedness. One may question that why not start with this particular thing. Historically, stability was discovered first, and then much later people realized that the same Lyapunov functions can be used for boundedness and things like that. And so we will present one simple result. So let me just basically flip through and then basically show the entire set of bullets here. So if we have this x of t, x dot of t is equal to f of x, and we will assume that Lyapunov function candidate satisfies the standard v of 0 is equal to 0. Here we are no longer dealing with time varying or something. We are back to time invariant systems. V of 0 is 0, v of x is positive for all non-zero x, and also radial unboundedness, v of x going to infinity as x tends to infinity, right? So if somehow v dot is less than or equal to 0, we automatically get global asymptotically Lyapunov stability, but we are not assuming that. Instead, we will assume that v dot of x of t, right? So v dot typically we defined as a function of x, but we are actually going, instead of x, we're going to put the trajectory, the actual solution of your x dot is equals f of x. If it satisfies this inequality, v dot is less than or equal to some positive number times exponential of negative number times time, right? Then we can show x of t is bounded, and then the proof is quite straightforward. So if you take this v dot is less than or equal to alpha times this, we get v of x minus v of x0 is less than or equal to alpha minus alpha of this thing, and then you can clearly see that this quantity on the right hand side is positive in the middle, and then of course that's further less than or equal to alpha times beta. So v of x of t at any point, the can call it as Lyapunov function evaluated at x of t is less than or equal to v of x0 plus alpha beta. Okay, I hesitate to call this Lyapunov function because typically that's only called it in the analysis of stability, right. So anyway, this v of x of t is less than or equal to v of x0 plus alpha beta, and v of x0 is positive, alpha beta is positive, so you have some positive upper bound. We use this positivity conditions everywhere. In reality, v of 0 is not used actually, but so therefore we probably don't need that. So, but how do I know? Just because v of x of t is bounded, can we conclude immediately x of t is bounded? That is where your radial unboundedness condition comes into picture, right? So, you should have v such that you cannot have x going off to infinity and still v remain bounded, right? The radial unbounded condition gives a contradiction, right? So therefore, you have to have boundedness of x of t, right? So, so this is a nice simple result, but the biggest drawback of this particular result is this condition v dot is less than or equal to alpha e times e raised to minus bt has to be checked on the trajectories. So if you don't have a solution, then this is a useless method, and if you have a solution, finding boundedness is probably easier through other means, right? I mean, still we may end up using something like this, but my point is basically it's almost impossible to get the solution. So in that sense, it's a nice result. It's an extension of the ideas of Lyapunov functions just to show boundedness, but unfortunately it has this inherent difficulty. So therefore, we will move on to another version, and then I call this as Lyapunov function method for ultimate boundedness. We'll get to that particular definition in a second. So once again, we'll consider the standard ODE, and again we'll have this assumption that there is a function v such that it's radially unbounded, but it is lower and upper bounded by class K functions like in our time varying theory, except there is no time here, time variation. And of course, we will assume that v dot is strictly less than 0, right? But not everywhere, In fact, away from the origin, around a ball mu, let's say. So outside some region, specifically outside some ball, we know that v dot is less than 0. So it's we don't need this v dot to be satisfied everywhere, but we unfortunately need that it is negative outside at least some region, right? And you can see the story here. I mean, it's relatively straightforward. Then, I mean, so essentially we have this ball. Outside this ball, v is behaving like a Lyapunov function. If you imagine this ball to be a point, then basically essentially we'll end up with stability theory for that particular set. Okay. So of course, and x of t therefore is going to be bounded, globally bounded for the matter, if all these conditions are global, right? I mean, it's possible that mu is small enough where this happens outside the mu, but there is a bigger region delta or something like that where these conditions are true, but beyond that they may not be true, in which case we'll get local boundedness. But if we have these conditions satisfied everywhere, then we'll have global boundedness, right? And we'll have globally bounded solutions, but much more through these conditions we can actually compute the ultimate bound, right? What happens as it approaches, as t approaches infinity, right? Now, I have this fancy notation called limb soup, and then let me just give an intuition in terms of what this limb soup is. Suppose you have a function that basically perhaps converging, rather decreasing in overall sense, but it's actually keep oscillating. So it keeps going up, but kind of settling to, say, let's say oscillation of amplitude 1 or something. So so we'll have this behavior of not limiting. It's not going to a single point, but yet we want to know the bounds, right? So the limits superior, or basically is basically for this particular kind of behavior. We'll take this maximum points of these two, the extremes, and then then call that as lim sweep, right? So in that sense, it settles down to some limiting behavior, and that limiting behavior is actually not a single point, but actually a bunch of points, and typically oscillatory behavior perhaps, and we will take the largest of that, farthest from the origin in terms of that particular oscillatory behavior, and then we have a bound for that particular behavior, right? So and then this is quite useful, and in fact the extension of this in terms of partial, in some cases, let's say imagine this x1, the part of the this thing actually could become your nice partial equilibrium and things like that. We may have theory to show stability with respect to that partial equilibrium, but the x2 itself may actually be bounded, and then we want to know the bound. We don't care so much if it goes to 0, but we want to know it's remain bounded, and perhaps in many cases we want to know what's the bound, and then this is the kind of theory we can do. I mean, this particular theory is meant for entire state, but you can actually extend this definition for partial stability on one side and then ultimate boundedness on the other side, right? And many times, especially if the second states correspond to some kind of control state and things like that, we don't necessarily worry too much about what happens to the control state. And these days, when we are implementing everything in a digitization format, those things do not probably matter, and it only matters that basically we have to have some kind of positive control throughout, right? So, but beyond that, basically, some of the states we don't really worry too much whether they are going to reach an equilibrium point and things like that. Okay. So, nutshell in terms of various versions, but let me actually kind of go through a couple of other extensions, so to speak, right? So, one special case we can think of is basically, let's say we have a system which lives only in this quadrant, and that's the non-negative quadrant, right? So in more general, in a higher dimension, we call that as orthant, okay, which comes from higher dimensions language. But anyway, so essentially this is the kind of system x belongs to R, where all xi's are greater than equal to 0. Okay. So the question is, there are many applications, quite interesting applications. The most important of those is anything to do with healthcare, where we model what happens to various chemicals, including drugs that we introduce into the system, how they behave. The concentrations and masses and things like that are always non-negative. And if we say model something like a thermodynamical system, we typically have temperatures and heat and things like that, and again they're all considered non-negative quantities. And even more complicated systems like financial systems, I call them complicated because there are no standard models. Even those, basically we'll have stock prices and things like that non-negative. So there are large number of applications, very crucial important applications, where we have this kind of restriction, right? One of the first questions we need to understand is basically, if we have the same old model, what kind of f guarantees non-negativity of x of t? Okay, and eventually turns out quite straightforward, though the proof itself is actually, as usual, quite subtle. But let me just demonstrate. Intuitively, it's fairly obvious, right? Let's say we have a two-dimensional system, and we are trying to ensure that f1, f2 are such that this the solution always remains in the non-negative quadrant in this particular case, right? So all we need to ensure is, if f1 of 0 comma x2 is greater than or equal to 0, and f2 of x1 comma 0 is greater than or equal to 0, then that's equivalent to x of t going to be greater than or equal to 0. So, if we have a dynamical system of this nature and we want to restrict our trajectories to non-negative quadrant, then we have the simple check in terms of f1 satisfying these two conditions. And then intuitively speaking, basically when x1 the variable x1 goes to 0, we don't want to go into negative. So, whatever if x2 side is going to actually push it away from the axis, right. So, that is the intuitive argument. Proving it is another matter. As always, we had difficulty in terms of showing existence of solutions. We had to go through this integral approach and things like that. Same kind of difficulties are here, right. So, now beyond working on the stability theory for these kinds of systems, first definitions itself are going to be difficult. Let us say you are trying to determine whether this particular origin is Lyapunov stable or not. Well, the fact is basically you do not have a ball around this origin. So, we have to restrict ourselves to not just the ball, but actually restrict it to the orthant, right. So, one has to extend and then be careful in terms of redefining your stability, and then after that Lyapunov function theorem works quite straightforward. But interesting thing is actually in this particular case one can consider linear functions as your Lyapunov functions. Typically we saw quadratic functions is how we start and ensure that they are Lyapunov function candidates and things like that, right. So, why? Because if we guarantee somehow non-negativity of these systems through these f functions, then linear functions also suffice. So, there is a very interesting entire set of theorems that can be derived for non-linear non-negative systems, and then they are of an independent interest, and we have an entire monograph on that, right. So, check it out if that is of any interest to you. So, the last thing that I want to briefly discuss is basically instead of looking at stability of an equilibrium, what happens if we have something like x dot equals f of x comma u. Typically when we have an external input, and let us say in this particular case that corresponds to some kind of noise, we do not have a control over it, just like we do not typically have a control over the initial condition. What can we say? We will certainly not have equilibrium, even though f of 0 comma 0 may be 0, right. But since we cannot control u, it will not remain at the equilibrium point. So, in that sense we cannot hope for Lyapunov stability or anything like that, because we do not have an equilibrium. What is the best thing that we can hope for? Well, somehow the solution of x of t is going to be perhaps bounded by some kind of class k function or something like that. I mean, sorry, some kind of function of the norm u, right. And of course, this kind of gamma function can be really bad in terms of this bound. Sometimes it can be quite straightforward and just simply a product, and then basically what kind of norm can we choose, what kind of gamma can we choose, can we minimize it, how small is this gamma, all those questions come up in terms of understanding the good nature of this particular system, right. But in the case of systems with inputs, this is the best we can hope for, okay. Interestingly, if the equilibrium point at u equals 0 happens to be asymptotically stable, we do have hope that it is input to state stable, and perhaps vice versa, right. So, those questions we will not address, but I just want us to understand that if we have inputs, then how do we handle the questions of stability, and this is the way to do it. Good thing, the best thing about some of these results is basically it almost seems like basically wanting asymptotic stability without this particular u seems to be a necessary condition, right. So, anyway, I mean, we will get to some of those details at a later point in a slightly different perspective, but for now we will leave this definitions and basic results of Lyapunov function theorems, right. So, what we have seen so far is basically just an analysis framework, and this is not end of the analysis. A lot more can be done, but the next 6 weeks or so is essentially extending or specializing, depending on how you look at it. It's kind of specializing the existing theory to something else, and then some extensions are indeed inevitable, and we will look at those extensions. And if we understand the basic theorem so far of Lyapunov function, rest of it is actually relatively straightforward. It's only extension of like I said, sometimes you can look at it both ways, extension or special case for various cases, right? And eventually we will end up talking about control and things like that, and then specifically optimal control. And each of these cases, the standard disclaimer remains, in the sense that we have this difficulty of finding Lyapunov function, and we will talk at the end how to perhaps completely get away from that kind of approach, right? Okay, so thank you, and then we will start a brand new topic in the next set of lectures.